Okay, so here's a weak example. We've got a string with a stone on the end, okay? So you're holding the stone essentially in the middle, and here's your stone, and it's going around in a circle. It's moving at a constant speed of 4 meters per second. So in a straight line it'll travel at 4 meters per second on a string length of 0.75 meters. Linear velocity at any point is going to be 4 meters per second. The angular velocity is going to be well, there's a couple of ways of working it out, okay, but essentially V equals R omega is one way of doing it to work out the angular velocity, or similar to that. Actually, there's a mistake in this. It should actually be 4 divided by 0.75, that equals about 5.3 radians per second. I won't change the notes, so hopefully you'll pick up on that. Okay, if you look at this, let's got degrees and radians. I'm going to explain the relationship between degrees and radians, okay, or really best thing to do is just learn how to define radians. Okay, 1 radian, or rad for short, is defined as the angle subtended at the centre of a circle radius r by an arc of length r. So in other words, the arc and the radius are equal, so S equals R in this case, and it's the angle that's there is going to be equal to 1 radian. So there we go. This for a complete circumference, 2 pi r is that distance around the circumference, and so if you think about this formula here and rearrange it, so let's make it theta equals S over R. So in this case we have got S and we have got R, so we're dividing S, the arc right around the circle, which is 2 pi r, dividing it by R to give you the angle. That will tell you that we have 2 pi radians in 1 revolution. Whenever you do questions, don't forget to write down radians and do not leave an answer as 2 pi. No, don't do that. Bad. Okay, so some important equations we've sort of seen. So we've got V equals omega. What else do we have there? We had S equals R theta. Alright, omega equals delta theta over time. Okay, a few more. You're going to have A equals V squared over R. And if you relate this to F equals ma, so it's going to be force equals mv squared over r. We're also going to have some more that we're going to look at later, but A could also be r omega squared, or F could also be mr omega squared. A couple others. For 1 revolution, the velocity could be 2 pi r, the circumference, divided by the period. Or you could have omega equals the total angle in the circumference divided by the period, and that can be rearranged to be also 2 pi f. So that's pretty much it for all the equations. So angular acceleration is if an object is moving in a circle at a constant speed. In this case, we've pretty much talked about it because the direction is changing and so on. There must be acceleration, there must be a force. So we're going to draw the formula. Consider an object of mass moving, and it moves from P to Q in time t. Okay, so we've got 2 vectors for the velocity. Okay, if you actually add them sort of together, you're going to get a change in velocity at the end there. Okay, so there's a change in velocity vector. Remember, it's final minus initial, so you can work that one out. And then you find that the change of velocity is parallel to P and O. Okay, when the theta becomes very small, we actually find that sine theta is very close to theta, so we can actually essentially get rid of the sine part of that and just put in theta. dividing both sides by t, that means that part there will be a change in velocity over time, which is an acceleration. And then on the other side, you're also going to have theta over t, which is omega. So A equals V omega in this case. Since we also have V equals omega r, okay, we can also then have that. So if we put in omega r for that V, okay, you can get V squared r. If you put in if you put in V over r for omega, then you can get that one there. And applying Newton's second law, you get two more equations. The important thing here is centripetal force, real force. Okay, you know, you're going to have things where you push on a block. Okay, so it could be a pushing force. You could have, remember, you get those charged rods. You bring it by some paper and it lifts it up. So that's sort of a electric force. Okay, those are different types of forces. There's not one where you're going to call it centripetal force. We actually use things like friction, electric forces, magnetic, gravitational, tension, to provide a centripetal force to go around in a circle. So examples on those: cars around a bend. Okay, so just driving around a curve, you need some friction to get around that curve to provide the force towards the center. Car on a banked curve. Okay, so here's a banked, so that's cross section of a banked curve. So it's driving around this banked curve like that. Okay, it can actually use the reaction force from the ground. So there's weight going down and there's a reaction force from the ground, and the vertical component would oppose the weight and the horizontal component would be your centripetal force. So it's actually the ground pushing up that provides the centripetal force. An object on a turntable, so you've got a couple of objects going around on a turntable, okay, around the center there. It's actually, these things want to slide off this way, at a tangent, what am I doing? At a tangent, okay, so they are going to push against the surface this way, and the surface is going to push back that way, and we'll call it friction. Okay, so it's the friction from the table pushing on the object is what's going to be keeping it there in circular motion. So there's a couple of worked examples. Okay, that should be 4 squared. Okay, put the things in, and you get the values. Okay, substituting some stuff in here. So omega, 1 full revolution is 2 pi. Divide that by the period, and then you get another equation. But also we know that t period is 1 over f, so that means you get 2 pi f. What we're going to do is look at the conical pendulum. Okay, so the conical pendulum is an important phenomenon that we'll look at in the next video.